Here is another sample problem. Okay, so actually it says the figure show the figure A. Figure A is, I think is this one. Figure A shows a cross section of a spherical metal shell of inner radius R. Okay. So actually, this one is the spherical metal shell of inner radius. Inner radius 就是内的半径，它是一个壳，就是有个厚度。OK， 所以它有内的半径，有外的半径。OK， so it says the inner radius capital R and a point charge of -5 mu c. -5 mu c. Actually, this one is located at a distance R/2 from the center of the shell. If the shell is electrically neutral, okay, what are the induced charges on its inner and outer surface? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay, the field pattern. Okay, so actually it is like, yeah, so simply speaking, the answer will be like this. There will be induced charges on the inner surface and also the outer surface. And actually so you may say that this is the Q inner equals +5 mu c, and the Q outer will be -5 mu c. Of course, these two values should add up to 0 because originally the shell is electrically neutral. The shell is electrically neutral, so which means that you cannot create or vanish the charges. So there are induced charge, but the whole metal shell should have a charge adds up to 0. Okay, and so that's why why Q inner to be +5 mu c is that if we assume Gaussian surface, assume a Gaussian surface to be this red circle, okay, which is in the metal shell, okay, just as what I mentioned yesterday, inside the conductor there should be no E field. There should be no E field. So if I just define the Gaussian surface to be like this, okay, so which means that according to there's no E field in the conductor. So when we try to calculate phi equals integration of E dot dA, okay, as much as there should be no E field, so this surface integral must be 0 because you are integrating at 0, so it must be a 0. Yeah. So in this case, phi is 0, which means that if phi is 0, which means that for this Gaussian surface, Q enclosed should also be 0. Yeah, because epsilon naught times phi equals Q enclosed, and phi is 0, so Q enclosed is 0 for this Gaussian surface. And actually this is the negative charge. This is -5 mu c, and as much as the Q enclosed should be something like a Q inner. Yeah. So this Q enclosed is equal to Q inner plus -5 mu c, plus -5 mu c. So E0 equal to Q inner -5 mu c, so which means that Q inner is +5 mu c, and in such a way Q inner plus Q outer also adds up to 0. So which means that this is 5 mu c, so this one should be -5 mu c, which is this number. Okay, so we have using the Gauss law, we are able to find the solution to the first one, which is the induced charge on its inner and outer surfaces. And it also asks, are those charges uniform distributed? and what is the field pattern inside and outside the shell. So it actually says that for the outer surface, the charge are uniform distributed. The charge are uniform distributed. However, for the inner shell, the charge are not uniformly distributed. Yeah, this is not easy to explain, but yeah. So I think for the second one, for the outer surface, the charge are uniform distributed is easier to understand, because when we try to apply Gauss law, let's say if we assume there is a Gaussian surface outside, okay, it will be somehow like there are totally -5 μc charges, and we will consider all the charge are somehow like concentrate at the center, and so it will be somehow like it is uniformly distributed. So and it will generate E field, okay, pointing to the center, Yeah, somehow like this. However, inside this metal shell, the E field line is somehow like that. So you will feel that for this side the E field is stronger, but for this side the E field is weaker. So in such a way, this side will have a denser charge density, but for the other side it will have a sparser density. And actually for the distribution, this is not easy to think in our mind. Actually, if you really need to know why it would be like that. So actually, I think it should be from some of this computer simulation. So it is not easy to explain why it be somehow like that. But yeah, actually this charges is somehow off the center. So it makes this side will have a stronger E field. And this phenomenon is interesting. It has a name called shielding. Shielding 就是它有一个像一个盾牌那样，就是说，我从外面看，我不是用眼去看，我看到这里有一个球壳，这里面有一个电荷在一个测的范围，我是在外面，我观测外面的一个电场的时候，我感受到的是，好像所有的电荷都集中在这个球心的位置。那然后我根本就感觉不到这个电荷是不是在中心或者是偏的所以这个就是像一个盾牌那样，我看不到里面那这个壳是没有电荷的，那我看到的这个就是负5 microcoulomb 的这个电荷被这个挡住了，那看起来就是这个负电荷在这个中心的位置，那就某程度上这个就挡住了我，但是它又不是完全挡住它。如果是挡住的话，它你应该是什么都没有感觉到，但是实际上你是感觉到有负5 microcoulomb 在里面的，这是我们叫做 shielding 的东西，就是我们让你看不到里面长怎么样OK， 那这个 so actually this sample problem is a little bit more difficult to explain. So let's go to the next section. So here we try to apply the Gauss law for some symmetrical structure. So we try to calculate the E field generated by some specific structure. So the first one is like the cylindrical symmetry. Okay, so actually when we try to apply the Gauss law, we really need to have some sort of symmetry, because originally the Gauss law is like integration of E dot dA times epsilon naught equals Q enclosed. Okay, so usually we will be able to know what Q enclosed is, and to see how the E field is generated. In that case, if we really can know Q enclosed, then we will be able to know this integration of E dot dA equals to Q enclosed over epsilon naught. Okay, so this is a known value, and actually this is an integration. Integration means we add many things together. If we know this is an integration, which means that it is like we add many E dot dA together. We add many things together, and we not know the sum. So if we would like to find what E is, so in that sense we should make all the E to be the same, or at least E could have some different value, but limit number of values. Otherwise, you may not be able to decompose it what it originally is. 就是那个意思，就是说，我们用这个高斯定律的时候，就是它是一个积分嘛，它是一个积分。那积分的话，你知道这个结果，就是已经是一个加总，它可能加起来10个数，加起来20个数，总和是多少？那最好是它只有一个值，它只有一个值的话，这个积分就变成一个乘法。那我就可以把它拆回来，就是变成说右手边除以那个面积就变成一个电场。如果那个高斯面上面每一点的电场都不一样的话，那我就知道它是11加12加13加14加很多等于一个数，那我没办法拆回来11等于多少，12等于多少，这大概是这个意思。所以我们就需要一些所谓的 symmetry symmetry 就是对称。对称的意思就是说，我们希望在这个高斯面上，它只有一个值，或者是两个值这个情况的话是两个值。它有一个是有电场的，有一些是没电场的。没电场就0嘛，有电场就是1，那它只有两个值，那我就可以去化简它。Okay, so actually it says a section of an infinite long cylindrical plastic， 就是一个长的椭圆形的一个塑胶棒。Okay, with a uniform charge density lambda. Okay, the charge distribution and the field have a cylindrical symmetry. Okay, 就是圆柱形嘛，圆柱形的一个棒子，所以它而且无限长的，所以它就是圆柱形的对称，就是你在这一点看到的是一根无限长的棒，那我在高一点的位置，我还是看到一根无限长的棒。如果它有限长的话，它就不是对称。所以的话就是说，它应该在一个圆柱形的一个表面，就是跟它等距离的表面都应该产生一个均匀的电场。Okay, so the charge distribution and the field have cylindrical symmetry. To find the field at radius r, we enclose a section of the rod with a concentric Gaussian cylinder， 就是一个同心的或者是同轴的一个椭圆，不是椭圆了，圆柱形of radius r and height h。 OK， 那我们就定义这个是一个 Gaussian surface， 半径是 r 啦，高度是 h， and the net flux through the cylinder from Gauss law reduced to something like this. Okay, originally, of course, we should have the Gauss law to be like this, equals Q enclosed. Okay, so epsilon naught is epsilon naught here, and yeah, here this one is actually phi. So phi for this cylinder. So we have we have, let's say, this side and this side. Okay, so for these two sides, E dot dA should be 0 because we know that the E field should be in radial distance. Okay, so in such a way, for the top and the bottom face, dA is pointing upward here and dA is pointing downward here. So for these two faces, E dot dA is like E times dA times cosine of 90 degrees, which is 0. So these two faces won't contribute to this surface integral. So only the side will contribute to this surface integral. Okay, and as much as this is a cylindrical symmetric, this rod is infinitely long, so we know that for the side, E always pointing to the radial distance, radial direction, I mean. And actually, it has the same direction as the dA for this point or for other points. It will be all the way E and dA should point to the same direction. So which means that E dot dA is actually E times dA, something like this. And we also know that as much as this is symmetry, so E is uniform over the whole side face. So which means we can also put this E outside the integral side. So which means that it is something like this, and then we can put this E outside. So finally, this integration of dA, which means the area of the side. Okay, the area of a side is easy to calculate, which is, so this thing is actually A. And for A, we can simply calculate as, so we try to cut this one like this, and then you try to expand it so it become a rectangle. So for the height, it is 2h, and then for this side, it is 2 pi r. Okay, because this is 2 pi r. So when you cut it out and then you try to flatten it, then it becomes a rectangle with a height of h, and then the width will be 2 pi r. So the area A will be h times 2 pi r, something like this. Okay, so here we have 2 pi r h for the area, and in such a way, we also assume that the charge, the uniform charge density lambda, the uniform charge density here, and yeah, so the Q enclosed is actually like the charge. Let me use another color. So it will be like the charge from here to here. Not a good color. So maybe I will just use a blue color. So actually, we consider the charge at this part. Okay, this is the Q enclosed for this part. Okay, so it will be lambda times h, will be the total charge amount inside here. So of course, for the whole rod, the charge will be infinitely large because this is a finite number, and multiplied by an infinite length, then the total charge will be infinitely large. But inside this Gaussian surface, the Q enclosed will be lambda times h. Okay, so in such a way, we can actually cancel h. Okay, so the height of the Gaussian cylinder is not important. Okay, it will cancel out. So finally, we can just move this 4 variable to the right side. So we have E equals lambda over 2 pi r epsilon, or 2 pi epsilon r. Okay, something like this. So for this equation, it means that the E field generated by this rod, this infinitely long cylindrical rod, is actually proportional to the charge density. So it makes sense because if you have more charges, they will generate a stronger E field, and it is inversely proportional to the distance from the rod to the point you concern. Okay, so it also makes sense because if you are far away from this rod, then the E field is weaker, and this is like a constant. So something like this. So any questions? Okay, so here we try to apply the Gauss law for the planar symmetry, 就是面的对称. Okay, so here it mentioned that it is a non-conducting sheet. Also, for conducting or non-conducting, it means that for non-conducting there is no free charge. So which means that the charge in this material is not free to move. Okay, it's not free to move. If it is a conducting, then the charge are free to move, just like this one. This is a conductor. So even though the total charge of this object is 0, but there can be some induced charge going to the inner face, and the opposite charge will go to the outer face, something like that. 这个所以可以产生那个叫做感应的电荷 induced charge。那非导体或者是绝缘体的话，电子是不能动的。Okay, so here it says a portion of a thin infinite non-conducting sheet with a uniform positive surface charge density sigma. Okay, sigma, a sheet of a thin plastic wrap uniformly charged on one side and can serve as a simple model. Here applying Gauss law. So this is the original Gauss law, and this is the non-conducting sheet. So it has a positive uniform positive charge density, surface charge density here. Okay, and actually this is a cross-section figure. So so here this is actually the thin. Okay, so although it looks not so thin, but here is that it is actually a thin thin stuff. So here we try to define the Gaussian surface to be this one. Okay, so actually include this part. Okay, but actually this is on the other side. Okay, this is on the right side, this is on the left side. Okay, so for the cross section it looks like this, and in such a way this is a thin sheet. So these charges will generate E field on both sides. Okay, on both sides. So here, as much as the charge is positive, so it will generate the E field pointing to the left side on the left side, and then it will generate the E field pointing to the right on the right side. Okay, if it is negative, if it is a negative charge surface, then the E field will point to the opposite directions. Okay, so so here we try to apply the Gauss law for this Gaussian surface. So for the side, so it will not contribute to the surface integral. Because for example, this point, the dA is like pointing, it has a 90 degree with the E field. So for the side, it won't contribute anything to this surface integral. So only this side and this side will contribute to the surface integral. And here as much as we know that this non-conducting sheet is infinitely large, so every point will see the same thing, so which means that on this Gaussian surface the E field is uniform. The E field is uniform. At least we know on this surface. We don't know the distance yet, okay, whether the distance is related to the E field yet, but at least on the whole, on the same surface with the same distance to the plate, okay, the E field should be the same according to the symmetry. Okay, so in this case, for this side, okay, so we assume the E field to be E, okay, which is a uniform value, and then this is the cross-section area A, and then for the other side, yeah, the value should be the same. So we have EA plus EA on the for this surface integral, and on the right side, the Q enclosed, the Q enclosed actually includes the charge here. Okay, actually include the charge here. So yeah, of course it is thin, so it is like sigma times the cross-section area. So it is like sigma times capital A. And then we can actually cancel this A. We can cancel all the cross-section area. So the radius of the cylinder is not important. And in such a way, we just move this epsilon naught and 2 on the right side, so we have E equals sigma over 2 epsilon naught, like this. Okay, so actually this result is actually the same as this result. So just as what I've mentioned yesterday. So for this one, in chapter 22, we try to calculate the E field generated by a charged disk with a radius capital R, and then we try to let this R to be infinitely large, so then this expression will be simplified into this one. But in that case, we don't actually apply the Gauss law here, so the steps it takes will be more complicated. You need to separate this into many rings with different radius, and then we try to integrate the E field generated by different rings, and then finally we get this expression, and then finally we try to let this R tends to infinity, and then it's simplified to this. So the computation is more complicated, but after using the Gauss law, so the step will be like 1, 2, and 3, and then done. So so that's why we need to learn the Gauss law in chapter 23 here. Okay. So so it says we have different ways to get the same result or same conclusion. Okay, so here we try to apply Gauss law for the planar symmetry again, and here we have two conducting plates. Okay, and this structure is quite important. Actually, what we learn in chapter 25 will be the capacitor, so which is one of the main circuit component. Main linear circuit component. Okay, so for circuit theory, there are 3 circuit components, three linear circuit components, which is like a capacitor, resistor, and inductor. So we'll learn it in chapter 25, 26, and 30. So actually, this structure is actually a type of capacitor. The capacitor in Chinese is called 电容。所以3个就是电容、电阻跟电感，这3个基本的那个线性的元件。Okay, so here we have 2 conducting plate. Okay, so first we just consider one plate of another. So for figure A, we try to consider. Okay, so just ignore the next one. Okay, the one in the figure B. Okay, So first of all, we just assume we have this this conducting plate, okay, with some thickness, okay, with some thickness. So in this case, we assume this infinitely large conducting plate with charge, with a charge, okay, with a charge. So as much as it has some thickness and and it is infinitely large, so all the charge will be concentrated on the left side and the right side only. There is no charges inside the conductor, okay. So we assume that the charge density on both sides to be sigma 1, okay, to be sigma 1. And in such a way, we will assume that the E plus will be sigma 1 over 2 epsilon naught on this side and on this side. Okay, just follow the idea here so that we can get this expression E plus on this side and E plus on that side. Of course, E is pointing to the left side on the pointing to the left on the left side, and then E is pointing to the right on the right side. And then we try to consider figure B. Okay, here we have the conducting plate with negative charge of the same surface density. It is still sigma 1, but a negative charge. So here we have a plate. Okay, so on the left side it is sigma 1, and then on the right side also sigma 1, but negative value. Okay, so on the left side we will generate E field pointing to the right, and on the right side we will generate an E field pointing to the left. And actually E plus and E minus have the same value, have the same magnitude. Okay, of course the direction are opposite. Okay, so here in the figure C, we try to put these two conducting plate together, with a distance. The distance here is not so important, so we just assume that here we have a positive plate, here we have a negative plate. Okay, as much as we place these two conducting plates close together, then the positive charge and the negative charge will attract each other. So which means that the positive charge will go to the right side and the negative charge will go to the right side. The negative charge will go to the left side. Okay, and yes, and the surface charge density will become double. Because originally half of the charge are on the left side, half of the charge are on the right side. So after the charge are attracting each other, so all the positive charge go to this side, which means that the surface charge density becomes double. Okay, so in such a way, E plus will be double compared to the uppercase. Okay, and similar E minus also generate 2 sigma 1 over 2 epsilon naught. Okay, which is double to this one. And okay, so here is like we try to add these two plates together, so that which means originally it's like it generates the E field, the E plus on the left side and E plus on the right side, and this is also E plus to the right side. And for the negative plate, it will generate E minus to the right side, E minus to the right side, E minus to the left side, E minus. Okay, so in such a way, these two cancels. So in such a way, there is no E field. There is no E field on the left side and no E field on the right side. There's only E field right between the two plates. Okay, so these two adds up. So finally, in the middle, we have E equals E plus E minus, and actually they have the same value. So actually we have the E field, which is 2 times to this value, which is 2 sigma 1 over epsilon naught. And here we try to define the sigma to be the new surface charge density, which means we define sigma to be 2 times sigma 1. Okay, so finally we just change this to sigma. So finally we have E to be sigma over epsilon naught. Okay, so this is actually a capacitor, which means that if we can make 2 parallel plates have opposite charges with the same amount, then it will generate E field between the parallel plate, and there will be no E field outside the parallel plate. And actually, between the parallel plate, the E field is uniform. Okay, it will be from the positive plate to the negative plate, and with a uniform magnitude. Yeah. So this is actually the simplified model for the capacitor. Okay, so here let's see a sample problem. Okay, so it says a portion of 2 large parallel non-conducting sheets, each with a fixed uniform charge on one side. The magnitude of the surface charge density are sigma plus for the positive charge sheet and sigma minus for the negative charge sheet. Find the electric field to the left of the sheets, between the sheets, and to the right of the sheets. Okay. Okay, so actually we can just use the equation in the previous page, which means E plus will be sigma plus over 2 epsilon naught, which means that half of it is on the left side, half of it is on the right side. Okay, so which means that for the positive plate, yeah, it will generate E plus on the left side to the left, and then E plus on the right side, which is pointing to the right. And then for the negative sheet, it will generate E field pointing to the right side on the left of it, and then the E minus will be pointing to the left on the right side. Okay, so in such a way we can try to compute E plus to be this one divided by 2 epsilon naught, which is 6.8 microcoulomb, which is 10 to the 6, and then over 2 times 8.85 times 10 to minus 12. Okay, so this number is 3.84 times 10 to the 5th power Newton per coulomb. Okay, and then for E minus, similarly, we have a sigma minus over 2 epsilon naught, which is this value. So it is 4.3 times 10 to negative 6 over 2 times 8.85 times 10 to negative 12. Okay, so this is 2.43 times 10 to the 5th power Newton per coulomb. Okay, so here we would like to find the total E field on the left side, between, and on the right side. Okay, so here it is nothing but adding these two together, adding these two together. But yeah, for the 3 parts, the direction of the E field are somehow different. Okay, so here we have a EL to be E plus minus E minus. E plus minus E minus. E plus minus E minus. And actually it is like a 3.84 times 10 to the 5th power minus 2.43 times 10 to the 5th power, which is 1.41 times 10 to the 5th power Newton per Coulomb. And for EB, EB is E plus E minus. Okay, E plus E minus. So it will be adding them together, which will be 6.27 times 10 to the 5th power Newton per Coulomb. And then for ER will still be E plus minus E minus. Okay, so it will be 1.41 times 10 to the 5th power Newton per Coulomb. And also we should also consider the direction, because to find the E field, which means that as much as this is a vector, so you need to answer the magnitude and as well as the direction. Okay, so for this case, EL, E plus is larger, so EL should point to the left side. And for the EB, okay, both E plus E minus are pointing to the right side. So this is pointing to the right side. And for this one, E plus is larger, so EB points to the right side. Okay, so this is a special case that the parallel plate don't have the same surface charge density. So in this case, it will generate a stronger E field between, but a weaker E field outside the parallel plate. Okay, so for the finish. So here we try to apply the Gauss law for the spherical symmetry. Okay, spherical 就是球面对称。Okay, so here we would like to use the Gauss law to somehow prove the shell theorem in chapter 21. And actually in chapter 21 I mentioned that we introduced the shell theorem, but we will not be able to explain why it is true, because for theorem we need to prove, but at that moment we will not be able to prove those two shell theorems. And here by the Gauss law we may be able to prove it. So let's see. For the shell theorem 21.1, okay, so it says the shell of a uniform charge attracts and repels a charged particle that is outside the shell, as if all the shell's charge will concentrate at the center of the shell. Okay, 所以这个意思是，如果我们有一个球壳它有一个均匀的电荷分布，那如果在外面的话，我们其实是看到所有的电荷都好像分布在中心一样。OK， 就是这里。那 OK， 所以 so here we can simply assume that the Gaussian surface is S2, so which has a larger radius comparing to the spherical shell. Okay, so here when we try to apply the Gauss law to surface 2, for which R is larger than capital R, larger than or equal to capital R. Okay, so here we have the R to be the radius of S2, and then capital R to be the radius of the spherical shell, or the charged shell. Okay, so we would find that E is actually this one. Okay, so the reason is simple. We can simply apply the Gauss law, which is something like epsilon times integration of E dot dA equals Q enclosed. Q enclosed is actually Q, and then for this one we are very familiar with it, which is epsilon naught times E times 4 pi r square, something like this. So it will be equal to Q, and then we move all these things to the right side except the E. So on the left side we have E equals 1 over 4 pi epsilon naught, and then Q over r square, which is this one. So yeah, according to Gauss law, it will be like this because yeah, this is uniform. So for the Gaussian surface, yeah, it is like spherical symmetry, which means that all the E field should be pointing to the radial direction and also has a uniform magnitude. So we can simplify this surface integral like this, and then we finally get this expression for the E field outside the spherical shell. And then for the second one, for the second shell theorem, it says that if a charged particle is located inside, okay, that is outside, okay, inside a shell of uniform charge, there is no electrostatic force on the particle from the shell, okay, so which means that here, for this case, we assume that S1 has a radius, okay, S1 has a radius smaller than the spherical shell, okay, in such a way when we try to apply the Gauss law, Q enclosed, okay, so in this way Q enclosed is 0 because all the charge are outside, so this is 0. And we also know that yeah, it is spherical symmetry because the charge here are uniform, so all the E field here should also be uniform. So in such a way, it is still like epsilon naught times E times 4 pi r square, and this is 0, and then all this stuff are not 0, so that we maybe cancel all these things, so that finally we get E equals 0 when r is smaller than capital R. So actually it is like using the Gauss law to prove the shell theorems in chapter 21. 所以呢，昨天有同学下课来问了，就是某程度上这个有点像循环论证，它就是Gauss law就是假设了一些东西，就是就是Gauss law就是假设它 Q enclosed 就只包括那个电荷在里面，就不包括电荷在外面。那好像已经假设了这个 shell theorem 的条件那样，但是这个是 Gauss law 了，定律就不需要证明嘛。shell theorem 是定理啊，定理就需要证明，所以用一个不需要证明的 Gauss law 来证明这个 shell theorem， 但是它们的条件刚刚好互相配对到。Okay, so here, so let's finish this part and then we have a break. So here we still also apply the Gauss law for the spherical symmetry. So here it has a spherical ball, okay, yeah, it has a sphere, okay, with a uniform charge density, okay, it should be like a volume charge density， 就是一个体积的，就是这个就不单纯是一个球壳了。For this case, this is just a shell, so the charge is only distribute on the surface， 就是这个是一个球壳，所以电荷只在那个半径的位置。那这个的话就是整颗球都是一个均匀的电荷分布，所以是一个体积的一个电荷密度。Okay, so yeah, so in this case we would like to find the E field generated by this structure. So for the first case it's like outside the sphere, which means that we assume that R is larger than capital R. Okay, capital R is this sphere. Okay, charge sphere, and we have Gaussian surface with a radius small r, and this small r is larger than or equal to capital R. Okay, so applying the Gauss law, yeah, which will be like epsilon naught integration of E dot dA equals Q enclosed. Okay, so Q enclosed is the whole Q, okay, because this sphere is smaller than the Gaussian surface, so Q enclosed includes all the charge. So this is nothing but Q, and then similarly the left side is still epsilon naught times E times 4 pi R squared, so I don't write it again, just the same thing. So finally we get the same expression here, okay, for the outside part. But for the inside part it is a little bit more complicated. So here for the second case, we assume the Gaussian surface like this with a radius r, which is smaller than capital R. So for this case, r is smaller than capital R. And the total charge is still Q, okay, the ball doesn't change, and also the charge amount doesn't change. But here, as much as the Gaussian surface is smaller, yeah, is smaller than the whole sphere, which means that Q enclosed is not Q anymore. It is actually smaller than Q. So here, what we know is that the charge density is uniform. So which means that we can obtain a ratio like this is the density. This is the density. So for the whole ball, Q divided by the whole volume of the ball, okay, which is a 4/3 pi r cube, okay. I think you should have learned it in high school geometry. So which is the volume of a sphere, okay， 就是球体的那个体积嘛，的4/3 pi r 立方。Okay, so when we consider the whole ball, rho is Q, the total charge, over 4/3 pi capital R squared, capital R cube. And then here we only consider the Gaussian surface, but it should have the same volume charge density. So Q enclosed divided by the volume of the Gaussian surface. Okay, so yeah, I mean the volume enclosed by the Gaussian surface. So it is like 4/3 pi small r cube. Small r cube. Okay, so in such a way we can make use of this part. Okay, so here we can get the expression Q enclosed, which is Q times R cube over capital R cube, because we can cancel this 4/3 pi on both sides. Okay, so the remaining terms are like this. So Q enclosed is actually this thing. Okay, similarly, we apply the Gauss law, and similarly, the left side look like this. And then for the Q enclosed, which is this thing putting here. So here we can actually cancel R squared and this R cube down to an R. And then finally, we just move 4 pi epsilon naught to the right side. So here we have 1/4 pi epsilon naught, which is K. And then on the right side, we have QR over R cube. Okay, looking like this. Okay, so the expression of the region outside the spherical charge ball and inside it is different. Okay, so inside it the E field is like linear to the radius, and outside it is like somehow like all the charges are concentrated at the center. So this is the different from this case. This case is only a spherical shell. Okay, so no charge are distributed inside the sphere. But for this case, the charge distribute uniformly for the whole sphere. Okay, so it still have some E field inside. Okay. Okay, so if we try to plot the E field according to the distance, so it will be like when R is smaller than capital R, it is proportional to the small r, proportional to small r, and after R is larger than capital R, it is like inversely. So this is proportional to R. This is inversely proportional to R squared. Okay. Okay, somehow like this, and then y at capital R. Okay, these two curves, yeah, actually have the same value. Okay, so let's have a 10 minutes break.